All right, well, welcome to the Ivy Online live lecture for Friday. We are looking at week 7. So for today, you should be hearing audio right now. And so you can check audio settings if you are not. And anyone who attends can participate by using the chat or raising hands and participating that way. So we are in week 7. And again, you should have posted in your class somewhere similar to this, an announcement or perhaps a link on the homepage that will take you to the live lecture schedule. And so I want to point out a couple things here at the beginning in that we are in week 7. So next week is the final exam. So we know a lot of students might be taking that earlier in the week. So we have adjusted our schedule so that we are changing the time. So I have a note here in the schedule that says we are moving the week 8 sessions that would normally be on Friday to Monday from 2 to 3 p.m. And the session that would normally be on Saturday is being moved to Tuesday morning from 10 to 11 a.m. And those are Eastern times. This week, we are still holding them at the normal time. So you're here today at this 12 p.m. session, and then we have a Saturday session tomorrow. So probably after Saturday, I'll actually just switch out these here so that it makes sense as to what session 1, 2, and 3 is next week. Again, looking at the topics for this week, we're looking at section 6.5, properties of logarithms, section 6.6, logarithmic and exponential equations, section 6.7, financial models, which are some applications that use exponential equations, and then section 6.8 on exponential growth and decay, and Newton's law, which again use some exponential and logarithmic equations to solve. As usual, the recordings will show up here. You can see the recording from Wednesday night is already here. The focus of Wednesday night was on all of the items, but primarily got through topics and problems with section 6.5 and 6.6 and a little bit of 6.7. So I think today I'm gonna kind of work backwards. Again, some of you have 2-day-a-week due dates, so you probably have likely already finished 6.5 and 6.6. I'm gonna focus primarily on 6.7 and 6.8. And then again, recordings will be added here, and there's a feedback form that can be filled out for anybody watching in a recording or here live. Next week is again, all preparing for your final exam. So I've got those times listed here that you can look at that are the new adjusted times. And there's a study guide. If you haven't seen this yet, your instructor may have posted it in your class, or an email may have come out to you giving you that final guide and some tips on how to study. So we're going to just kind of summarize a few things here. I'm not going to do problems from 6.5, but I want to mention the logarithmic rules from section 6.5, because I'll be incorporating those in the examples that I do from 6.6 and 6.8. So some of these rules are on the formula sheet, some of them are not. So I really highly encourage you to make sure you look through this list. And I just pulled this from the textbook, basically, in the material in your module. So I just kind of condensed out, hey, what are all the rules? So we've got a change of base formula. We've got some properties of one-to-oneness that allows you to take a logarithm on each side or to remove the logarithms on each side of these single log statements. And then kind of the 3 big ones are our product rule, quotient rule, and power rule for logarithms. And then we've got some properties that work here because these are inverse functions of each other with exponential and logs with the same base. And then some special rules up top here. So I, again, encourage you to look at the formula sheet. I have a copy of it here. So you know what isn't on here so that you know what to study and learn and not rely on the formula sheet to have it. And then the things that are on the formula sheet, you know, just kind of focus on making sure you know how to use them. So you can see here primarily the stuff from these 6.5 section. This 6.5 section is this set of rules at the bottom. But you can see not every single thing I had kind of on the screen there is there. And then 6.6 is basically kind of applying some of those things. The big thing to remember is our definition of a logarithm. If you have it in log form, you have a statement that is y equals log base a of x. And then you can swap that and change that to exponential form using this definition of a logarithm, because basically remember, a logarithm represents that exponent y when you are looking for the inverse function. When you've got your exponential function, you've already swapped your x and y, you need to solve for that. And so that's what the logarithm is defined as. That's used a lot in solving logarithmic equations, is to switch from log form, what I have highlighted in yellow, over to exponential form, what I have highlighted in blue. Again, just some tips on some strategies to use for solving logarithms. Think about what you have. If you have the equation written in one of two ways, it could be written in the format of you have a single logarithm of a quantity equaling a value, some constant on the other side. If that's the case, then you're going to do option 2 here, and you're going to change to exponential form to switch how this equation is written, and that's using the definition I was just talking about. But if instead you've got a logarithm of one quantity on one side equal to another logarithm of another quantity on the other side, then that's a time where you're going to do what's listed here in number 3, where you've got these two independent logarithm terms on each side. As long as it's the same base, you can remove or drop the logarithms and set the exponent, or not the exponent, set the inputs to the logarithm, the something and the something else, equal to each other. And that's that one-to-one property allows us to kind of remove the logs. So it depends on how it's written as to which format you do. And then of course, you can always check your solutions and always be mindful of the fact that there's a domain restriction for logs, in that the input to the logarithm always has to be greater than 0. So there's are just some of the basics for solving log equations. I'll use some of that today and some of those properties. In section 6.7, that's when we get into the financial models. We've got simple interest. We've got different payment periods. Make sure you understand, if it says semi-annually versus quarterly versus daily, et cetera, what that means in terms of the number of payments, because all of those tell you the n value. So n is either 1, 2, 4, 12, 365, et cetera, for the value in your compound interest formula, which I have down here. And so those values, 1, 2, 4, 12, 365, et cetera, are replacing n, which is telling you how frequently it is compounded or calculated each year for the interest. And you're looking to see, does it tell you in the problem that it's compounded a certain number of times per year? That's how you know you're using this compound interest formula. The other big thing to remember is your interest rate is always expressed as a decimal when you use it in the calculation. So if they tell you the interest rate is like 5%, you're not actually using the number 5, you're using 0.05, because that's the decimal equivalency of the 5%. And then you could have something where it tells you that it's compounded continuously. So if you see the word continuous or continuously, well, then that's a different formula. And that's often what a lot of people refer to as the PERT formula. It kind of looks like the word PERT. And so that's using a base of E. Whereas in the compound interest formula, your base is actually this expression that's in the parentheses, 1 plus your rate divided by the number of times it's compounded. And likewise in the PERT formula, you want to express the rate as a decimal. We've got a couple extra formulas for effective rates of interest that are in that section, and an extra formula for what if you wanted to find the present value of something that you know you need to have a certain amount in the future for, like what do you start saving now to get a future amount? Those formulas are actually kind of optional. It's an extra formula. One thing to point out in them is that there is a negative sign on the exponents in those. And basically what has happened is the A and the P have swapped from the formulas up here for the future amount of something when you know what you're starting to save with. But I'm going to work through some problems today showing you where really you just need these two formulas for compound interest and continuous compounding. You don't really need these extra formulas for present value. They're in the textbook and the e-text, and they're in the section, but you can work without them. And you'll notice if you go back to the formula sheet and you look at what formulas are on here, those extra formulas are not on here. So it's really best if you know how to work with the formulas that are on here and not, stress yourself out trying to memorize more things. And then, since I'm talking about formulas, in section 6.8 that we'll talk about, this is about uninhibited growth or decay. So something growing or something shrinking basically over time. It has to do with a lot of things found in just natural life, bacteria growing, things decaying over time naturally in different elements and things like that. The basic formula is given by this formula with the A's here. You'll also see it written in the book with an N. So you'll see here, it's essentially the same formula, except that they're talking about growth of cells. So in this case, K is always positive. But if I was talking about decay, it doesn't matter if I call my amounts N or A. It's really the same formula. What's different is we're changing whether K is positive or negative. So when it's decaying, K is negative. When it's growing, then K is positive. Otherwise, it's really the same kind of formula. So again, whether you call it A's or T's, doesn't matter so much. So if you go back to the formula sheet, you'll notice it's only on here once. It's on here with the one statement with N's. N of T is the future amount, N sub 0 is your initial quantity that you're starting with, and then times e to the KT. And then we just designate whether K is positive, it's growth, or K is negative, then it's decay. But rather than memorizing multiple formulas or referring to multiple formulas, you can just do that. And then that's it for the formula sheet. So again, there are other formulas that are in the section that you might use in some of the homework problems, but they're not necessarily on here. So anything else that's not really on here, you probably want to learn and know, to refer to. Then we've got Newton's law of cooling that's used in some of your homework problems and things, which again has e to the KT. So it's an example of something that uses the base E formula. So I'm going to try and go through as many problems I can here and also give you some tips on using the calculator. So that's another big issue in these sections is it's great to have the formulas. You've got the formula sheet. You can plug numbers in, but ultimately you still have to get it into your calculator correctly. And that's where I see sometimes a lot of students will go wrong. That's why it's also really important to show your work. So again, at your test, you are putting your work on paper and you are either going to scan and submit that to your teacher in Ivy Learn, or if you're testing at a campus testing center, the attendants there are going to collect your work and they're going to scan and send that back to your instructor. So you may have a problem completely written out correctly. You've done all the steps, and then it gets to the point where you have to put it in the calculator, and then you get the final answer wrong, showing in MyLab. That's where it's really important for your instructor to see your work, because a calculator entry mistake, most likely, I won't speak for every instructor, but most likely is, not as severe of a mistake. And if you've got everything on your paper correctly, your instructor most likely will give you back some partial credit of different amounts per instructor for that. So I'm going to take a look again at as many problems as I can to show you some different things to look out for with what you're working with. So this problem I liked because it actually requires you to use the two different types of interest problems or interest formulas for compounding and also for continuous. So we're going to compare this. So again, I grabbed a problem and I have the answers. It's more about, how do you get it? So that's what I'm going to focus on. So what we have here is Trisha is investing $6,000 and Sean is going to invest $6,000. But Trisha is going to put hers into something that's compounded quarterly, and Sean is going to put his into something that is compounded continuously. So they both have the same starting amount of 6,000. So that's the principal amount for each of these. The interest rate is slightly different. So let's list this as Trish and Sean. Actually, I'll do Sean in a different color. So they're both starting with $6,000, but Trish has an interest rate R of 6%. So we're gonna make a note to write that as 0.06. And it's compounded quarterly. Quarterly happens 4 times a year. So that's telling us that N value that I talked about earlier of the different words and how many times per year each one represents. And then Sean, on the other hand, has a slightly different interest rate of 5.9%, which as a decimal, you want to make sure you're writing that correctly, is 0.059, and then compounded continuously. So there is no N value for compounding continuously because the formula is A equals P times E raised to the RT, or the PERT formula. And so there's no N in there. We want to know who has more money after 20 years. So that means the time frame is 20 years for both Sean and Trish. So if I put my formulas together for each of them, for Trish, the future amount is the principal times 1 plus the rate divided by the number of times compounded, raised to the compounding time times the years T. So I'm going to substitute things in. So the future amount is $6,000 times 1 plus the rate as a decimal, 0.06, times the number of times compounded, 4, raised to, and now notice what I'm doing. I'm putting the exponent in parentheses because it's a product of N and T. And so this is 4 times 20. I could put this in my calculator now. Everybody should be using a scientific or a graphing calculator for this class. And they are designed so that you can put things into them as a calculation with multiple steps and operations and parentheses and exponents without having to continuously put one thing in, hit enter or equals, and then retype that in and put something else in. You can get rounding error if you try and put things in multiple steps. It's really to your advantage to learn how to use your particular calculator so that you can put it all, say, in one step. So I am going to make this slightly easier. The 4 times 20, I am going to write as 80. I would not rewrite anything that doesn't multiply or divide nicely. And by that, I mean it's a terminating quantity. If something is a repeating quantity, or it looks like it goes to the end of your calculator screen and it doesn't stop, you don't want to use it in that way. You want to keep it in its exact state, exact form, like with a fraction, and not do any rounding until you get to the end of something. So I should be able to put this in my calculator exactly like this. I should be able to enter 6,000 times, that's what the parentheses means, and then literally open a parenthesis. So again, all of your calculators that are scientific or graphing should have parentheses on it. And then 1 plus 0.06 divided by 4, I can put it in literally as exactly how I'm saying it. 0.06, use your division key, and then divide by 4. So you don't need any fancy fraction buttons. If you have a calculator that has a fraction button, then you can certainly put 1 plus and then hit your fraction button to do 0.06 over 4. But if you don't have a calculator that does that, then literally the fractions are just division. So just use your basic division key for that. Close your parenthesis, and then to get your power, remember that you are using your caret key, basically, or some calculators might have an X to the Y key, whichever type of button your calculator has. And so then I'm also going to pay attention to the rounding rules. So this says to round to the nearest cent as needed. And so we are going to round. So we get approximately $19,743, and I get 0.976. So I'm going to write that as 0.98. And so that's the amount that Trish would have. And you can see that matches what's here. As for Sean, he's using the PERT formula. So for Sean, his amount is going to be his principal 6,000 times E raised to, again, I'm going to put this in parentheses, R, which is 0.059 times 20. So again, I could enter it exactly like this using my caret or my E to the X key. It should open a parenthesis, and then I can literally put in 0.059 times 20. If you are uncomfortable with that, by all means, you can take 0.059 times 20 first, and I can instead enter this as 6,000 times E raised to the 1.18, because that's what 0.059 times 20 gives me. So that's a nice terminating number. So that's okay to rewrite that. But again, that's an extra step. And if you are someone who always runs out of time at the test, you don't want to be taking extra steps. You want to work smarter, not harder. And so use your calculator to your advantage to know how to use it properly. So you can put it in exactly how I have it written in the first way or the second way. Either way, 6,000 times, and you use that E to the X key, which you get by doing a second and then your LN key, most likely, again, depending, I'm having trouble writing and talking at the same time. You most likely, there we go, hit your second and then LN key to get the E to the X key. And then it would put a caret in a parenthesis, most likely, and then you put in your 1.18, or you put in your 0.059 times 20. Either way, and close your parenthesis for that. And so this one we're also rounding. So 19,526. I get 0.245, so I'm going to write that as 0.25 rounded to the nearest cent, and that would be the amount for Sean. So it asks which one has more money. So you compare the two numbers. And so 19,700 versus 19,500 something, this is more, so Trish has more. And that's what we see here, okay? So again, this is a nice problem showing multiple formulas, compounding continuously, quarterly. If quarterly was like monthly, then the N would change to like the number 12. If it was daily, the N would change to like 365. But it's the same formula to start with, and then just comparing answers and seeing who has most. Here's an example where I was talking about what I just showed you was showing a future value. So the future value for Trish and Sean, if they're saving a certain amount of money. But you can also say, well, I know I want to have a certain amount of money in the future. Like maybe you have a savings target and you know you want to have a certain amount of money saved, 5 years from now to make some larger purchase. What do you need to start saving today? Well, that's called a present value. So I mentioned at the beginning that there are separate formulas for that, but those separate formulas are not on the formula sheet. And you can solve these problems for present value without using those extra formulas. You can just use the standard compounding continuously and compounding n times formula. So I have two different problems, number 5 and 6, because this one is for compounding quarterly and 6 is for compounding continuously. So again, trying to show you kind of both ways. So it says to find the principal needed now. So that means we need to figure out what is that principal P. We don't know what it is. That's our present value to get $200. So that means that's our future amount of $200. And our time frame looks like it is 2 years. And our rate looks like it is 6% or as a decimal 0.06. It's compounded quarterly, so N is 4. And so for that, we want to make sure that we are putting things in the formula correctly. And so we are going to just start using our normal compounding formula and not the special formula. So remember, the future amount is principal times 1 plus the rate divided by the compounding n raised to the compounding times t. I like to put those in parentheses. So plug in everything you know. You know the future amount is 200. You don't know the principal p for the present value times 1 plus the rate of 0.06 times 4 for the compounding periods raised to 4 times 2. So I've got it all in. Now I can kind of simplify some things. The 4 times 2 I can write as 8. So this is 200 equals p times 1 plus 0.06 divided by 4 raised to the 8th. Now, you might be thinking, well, can I just take the 0.06 divided by 4 and add that to 1? In this case, you could, because if you take 0.06 divided by 4, you get a terminating decimal. You get 0.00 or 0.015. That's not always going to terminate. So for example, if I had a different rate, like, I don't know, 0.05, because I had a 5% interest rate, and my compounding was monthly. If I take 0.05 divided by 12, I get a repeating decimal. So I would not want to redo that. So I'm going to leave it written as it is, even though this particular one can simplify, just to show you what it would look like when you can't simplify it, because that will happen depending on what your numbers are. So you want to solve for this value of p. It is currently being multiplied by everything that I just boxed in, that is the parentheses of the 1 plus 0.06 divided by 4 raised to the 8th. So just think opposite operations. It's multiplied by p. So to solve for p, you divide on each side. So our calculation would be 200 divided by that expression on the right, 1 plus 0.06 divided by 4 raised to the 8th, and that will give us p. And that's what we would want to put in our calculator. So again, you have a scientific or graphing calculator that should allow you to use parentheses, raised to a power of 8, and you should be able to put it in exactly as it's written here. So 200, that bar for division is literally your division key. And then I can put in parentheses 1 plus 0.06 divided by 4, close my parentheses, and then to get to the power of 8, again, you're going to use your caret key or your x to the y key, depending on your type of calculator. And then pay attention to any rounding. It says nearest cent. And so that should all give you the 177.54 when you round that. And it does. Okay, you get 0.54 and then some 2s. And so that rounds to a 0.54. And so I didn't have to use any special formula. I just used the regular compounding formula, okay? If you wanna use a special formula, you can. It's slightly different. The A and the P swap. So you're directly just doing a calculation and then the exponent is negative. But again, you'd have to remember that because that's not over here on the formula sheet, right? We just have the original one. So, it might be best to just learn how to do it with the original formula. All right, so then for comparison, for number 6, this one's doing compounding continuously, but it's the same concept. We're solving for the principal amount or the present value. So what we know here is we need to find the principal, so we don't know what P is, in order to get $90. So the future amount is $90. We know we're doing this for a time frame of 3.5 years. I'm going to go ahead and write that as a decimal, so 3.5. And then we know our rate is 8%, which I'm going to convert that to a decimal equivalency of 0.08. And the fact that it's compounded continuously tells us to use our amount equals P times E raised to the RT formula or our PERT formula instead. of the compounding end periods formula that we just did from above. So I'm going to just substitute things in like I did before. And so this means I've got 90 equals the principal that I'm solving for times e raised to 0.08 times 3.5. I'm using a dot for times there. So again, this is a case where it might be best to try and multiply the r times 3.5 for the time frame. So the 0.08 times 3.5, and then I can write that as 0.28. So 90 is my principal times e to the 0.28. And so again, think about what's happening here. The p, present value or principal, is being multiplied by e to the 0.28. So I can divide on each side so that my calculation is 90 divided by e raised to the 0.28, and that will solve for my present value. And so again, you're putting this in your calculator. That bar means the division key, and you're going to use the e to the x key, which is usually given by second and ln to get that. And so 90 divided by e raised to the 0.28 is going to give us, with rounding to the nearest cent, 68.02. You actually get 68.0205 something. And so because it's followed by a 0, you get 0.02. So that's how, again, you can do that without using any special different formula. You're just considering, how are you solving for that present value? And again, it's just multiplied by that other quantity. So you divide by that on each side, depending on which formula you start with. Another example of the typical type of problem you might see is doing something where you want to take an amount of investment and you want to say, multiply it out to a bigger amount by either doubling, tripling, quadrupling. There's, different ways to say it, but typically the most common are doubling and tripling. So here's one where it's asking you to double an investment. But they want to know the rate for which you use for that. So it says what rate of interest. So that means we're looking for finding R compounded annually. So that's telling us that n equals 1 is required to double an investment in 6 years. So the time frame is 6. So if you think about doubling an investment, then if you start with P, then doubling gives you the future amount A equaling twice P. So let's just reason it out with numbers. Like if you start with an investment of $100 and you double, then your future amount is $200. If you start with an initial amount of $500 and you double, then you are starting with 1,000, and you get that by taking 2 times your principal. So if this instead said triple, then if you start with P, then the future amount is 3P. If it's quadruple, for example, then you'd have P and 4P and so on and so forth, okay? So what this tells us is this is compounding annually, that's 1 time a year. So I can use my compounding formula of future amount A is principal P times 1 plus my rate divided by the number of times it's compounded raised to the number of times compounded times the time frame. So what do I know? I know that the future amount is twice the initial amount, even though they don't tell me what the initial amount is. So that I can replace that with 2P where there's an A. And then the initial amount is still just whatever P is. I don't need to know the actual dollar amount. Times 1 plus my rate, well, that's what I'm trying to find, divided by the number of times it's compounded, well, that's a 1. If it said semi-annually, then that would be a 2. If it said quarterly, that would be a 4. raised to 1 times 6 for my time frame. Now I can simplify this a little bit. 2p equals p times r divided by 1 is just r. 6 times 1 is just 6. Now you have to remember what we're trying to solve for. We're trying to solve for r. Well, I've got this extra variable of p. Well, if I divide by p on each side, that removes the p from the right because it's just multiplied by this expression 1 plus r to the 6. It also removes it from the left, which is good because now I'm left with one equation, or excuse me, one variable in my equation, which is what we want. So now I got to think about, well, how do I solve this? I've got 1 plus r raised to the 6th power equaling 2. I need to solve for r. How do I undo a power of 6? Well, there's 2 different ways you can do it. You can take the 6th root on each side, okay, which tells us then that we would have the 6th root of 2 equaling 1 plus r, because the 6th root undoes a power of 6. Or, I'm going to write this repeated here, or the other way you can do this, so this is take 6th root, or the other way is raise it to a power that results in a power of 1. So basically, whatever your power is, raise it to the reciprocal of that power. So I could take all this and raise to the 1/6 and then do that on the other side. So I could raise to 1/6. So if I had this 1 plus r to the 4th power, then I would raise to the 1/4. If I had this 1 plus r to the 10th power, then I would raise it to 1/10. So in doing so, that negates your power. So that's really a power of 1, which gives you just 1 plus r. And then now you've got 2 to the 1/6. If I'm going to do it that way, I would put that 1/6 in parentheses in my calculator for the exponent, which again, I would just enter literally as a fraction, 1 divided by 6, literally using my division key if I don't have a special fraction button on my calculator. So now, again, I'm solving for r. So in both of these cases, whichever way you decide to do it, 6th root of 2, I'd have to subtract 1. That gives me r, or 2 to the 1/6, subtract 1 gives me r. So either way should give us the same answer. Now, remember, we're solving for r. R is a decimal in the solution, or in the calculation, I'll say. In the calculation. Okay. And so for the calculation, r is a decimal. But for our solution, we want to have a percentage. Okay. And so for that, we want to take whatever answer we get here, it'll be the same answer, and convert to a percent by multiplying by 100. So that's important here, because when you're solving, you're just going to get a decimal representation. To do the 6th root, you might have a key on your calculator. It may look differently depending on the type and brand of calculator that you have, but you can use what looks like an X root key. So I would put in 6, then I would hit my X root key, and then I would put in 2. I have that button on my calculator. Alternatively, I could put in 2 caret parenthesis 1 divided by 6 and close that. And that I could do it that way. And then for both of these, I have to still subtract 1, okay? So it doesn't matter which one you do, but if you are gonna do the power of 1/6, you do wanna have that in parentheses and then subtract 1. And so that gives me, in each of these cases, that r is approximately 0.1225 2462048, and then it's going to continue on my screen. But I need to multiply by 100 and then do my rounding to 2 decimal places. So if I do that, then I get 12.25, because this is going to shift this decimal point over 2, and the 6 is going to bump the 4 up to a 5. And so that's how I get 12.25%, which is the answer that's here. And the percent sign is already there, so you don't have to enter in the percent sign for that, okay? So that's, again, a way to do something with doubling, tripling, et cetera, but also how do you take and undo a power that isn't like, a lot of people know if you have a power of 2, you take a square root, but what do you do if it's a different number? Well, then you take that nth type of root. So look for that nth root key on your calculator, or if you don't have that, a quick, easy way to work around that is raised to the reciprocal of the power that you have. All right, I think in the time that we have, I think I'm gonna jump to section 6.8 to do some examples with that. So let's take a look at an uninhibited growth problem. And so let's say, let's see, which one do I want to do based on the time that we have? Let's do 24. So, because I don't think I'll have time to do all of them. So on 24, we are given information that says we have a population and it's following the exponential law, and then use this information to answer these questions. So in part A, if N is the population of the city and T is the time in years, we want to write N as a function of T. So that's really just getting you to recognize the formula. Remember, the formula can use N's or A's, but this says type an expression using T as the variable and in terms of a base E. So again, N sub 0 is your initial population. T is your time, and K is a constant that's going to end up being a growth factor or growth rate. And it's not provided to you, but so this is just asking you to type in the, the generic formula that you're using. Then in part B, we get into the nuts and bolts of what we have here. So it says if the population doubled in size, so the population doubled in size, so it's twice as large, over 26 months. So that's the time frame. Notice that says months. It does not say year. In part A, notice that time was in years, but in part B, we're in months. So what we can do is we can adjust this formula for months to say that the future amount N of T is the initial amount N sub 0 times E to the K times T divided by 12. Because if T is in months, to convert months into years, I would divide by 12, okay? So I can make that adjustment there. And then it says the current population is 20,000. What will the population be 2 years from now? So I want to first focus on, we need to solve for K. So we need K first. So what do I know? We know if the population doubled, so N of T would be twice the initial population. And that happens when T equals 26 months. So what I know is that twice the initial population, N sub 0, equals the initial population, n sub 0, times e to the k times 26 divided by 12. Now that's one of those cases where if you look at 26 divided by 12, it does not divide equally. So like I mentioned before, like you don't want to round that anywhere. Notice that this warns you to not round anything until the final answer. And then when you finally get done, you're rounding to a whole number if you need to. So I'm not going to round anything. So I'm going to leave the fraction 26 over 12 there and not try and write a decimal for that. You will get rounding error and answers wrong if you try and do that. So I want to solve for k. Oops, I need my pen, not my highlighter. So we're going to solve for k here. Okay, so I can divide each side by n sub 0, and that removes this. So I have twice equals e to the k times 26/12. So at this point, I can do a couple different things. I can use my definition of a logarithm to convert from this exponential form to log form, or I can look at that and say, oh, well, I can use the one-to-one property with exponentials and apply the natural log of each side. And so I'm going to choose to do that. I'm going to apply the natural log to each side, okay? And that was using this property here that I can actually use forwards and backwards. I can say if m equals n, then I can apply the logarithm to each side. And that's what I did. And so in doing so, using some of our log properties, we know that basically what that does is the natural log being base e of a base e raised to a power gets rid of this and just brings this down so that I have the natural log of 2 equals that power. So this is 26/12 times k. So if I want to solve for k, I can just divide by 26/12. And if I'm going to divide by a fraction, that's like flipping and multiplying by the reciprocal. So this is really 12 times the natural log of 2 divided by 26 is my exact representation of k. So this is my exact value for k. So now what I know is that this formula we know is now the future amount n of t is equal to the initial amount, which is the current population, 20,000 people, times e raised to this value of k. So this is 12 times natural log of 2 divided by 26 times t. And actually, just put it times t there, okay? And so that's what I know. And so we want to know, what will the population be 2 years from now? So I need to plug a 2 in for t. So this means, oops, n of 2 is 20,000 times e raised to 12 times natural log of 2 over 26 times 2. So I could clean that up a little bit if you want to make it easier to put it in your calculator, but it may not clean up for every problem. So you could just enter it like this, but I am going to take the 2 times the 12 and make that 24. So this is 20,000 times e raised to the 24 times natural log of 2 divided by 26. So you just have a fraction as your exponent. And you should be able to enter it the exact same way that I have written here, so that when you use your e to the x key, in parentheses, this entire fraction with a numerator of 24 times natural log of 2 is then divided by 26. And you close that parenthesis for your exponent to evaluate that in your calculator. And they told us to not round until the final answer, but round to a whole number. And so if you do that correctly, you should get 37,923 people, which matches the answer up there. Okay. So again, you know, think about, yes, are there ways you can simplify things, but don't simplify too far because you can get into the weeds with that and not be able to do that well. All right, I think I have time to start setting up. We might not be able to solve the whole thing, but set up a Newton's law of cooling problem. I think you have a few of these in your homework assignment. This uses a totally different formula. This formula is not on the formula sheet. It is in the section material, but I'll go ahead and write our basic formula here. So U of T is capital T plus U sub 0 minus capital T times E raised to the KT, where K is something less than 0 here. So what are all these things, what are they all representing? So the capital T is the basically room surrounding temp. Wherever the object is, what is the surrounding temperature around it? U sub 0 is the initial temp of object that you're dealing with. So let's kind of look at what's happening here. A pizza pan is removed at 10 p.m. from an oven whose temperature is fixed at 425 degrees. So if the oven is 425 degrees, presumably when you take the pizza out, the pizza is 425 degrees. So this initial temperature of the pizza is 425 degrees Fahrenheit. Into a room that is a constant 71 degrees Fahrenheit. So that tells us our capital T is 71 degrees Fahrenheit, okay? And so then it says after 5 minutes, the pizza pan is at 300 degrees. So after 5 minutes, that means U of 5, so the temperature 5 minutes later, is 300 degrees Fahrenheit. So what I initially know is that U of 5, which I can just write as 300, is equal to the temperature of the room, 71, plus, in parentheses, the initial temperature of the pizza when it came out of the oven, that was the 425, minus the temperature of the room, times E to the K times T. Well, T was 5 minutes later. So notice I have everything in there but K. So this is another one of those situations where they don't normally give you the constant value K. You have to find that first, okay? So I can simplify things. 425 minus 71. I can simplify, and that's going to be 354. I can also subtract 71 to the other side. So 300 minus 71 is 229. So what I'm left with is 229 equals the 354 times E to the, I'm going to put 5K, with the 5 times the K first. So I can now divide by 354 on each side. And that gives me something that is not going to divide nicely as a whole quantity. So I can leave it as a fraction, 229 over 354 equaling E to the 5K. So if I want to solve for K, okay, this is where I can do what I was doing similarly in the last problem. I can either use my log definition to switch from exponential form, which it's in now, to log form, or I can apply the natural log to each side. I like personally to apply the log to each side. That's just how I like to do it, but either way will work, because when I apply the log, I can see that these two items, natural log and base E, negate each other basically because they're inverses, and that allows me to drop down this 5K not being an exponent anymore, and that is all equal to the natural log of this fraction 229 over 354. So now I can divide by 5 on each side to solve for k. So my k representation is natural log of 229 over 354 over 5. At that point, I can now say my equation is U of t is my room temperature, 71 plus 354, which is what we simplified the room and the pizza minus the room, times E raised to, I can leave this as a fraction or I can write this as 1/5. 1/5 natural log of 229 over 354 times T. And then I can use that to continue doing the rest of the parts by plugging in specific T values to solve, or the U of T values. So like if the pizza is 125 degrees, then I'm swapping out U of T for 125 and then solving for T, and then looking at the time frame, for example, for part A. But again, without solving for K first, you can't really get very far in the problem. So we're right at the time to end. So I want to remind everybody that back in the live schedule, which again is linked in your course, a recording for this will show up later, and there's still one more session tomorrow from 2 to 3. Anybody who is also, either here now or watching this in the recording, you can submit a feedback form if you want to. It's optional, but we appreciate that. And then next week, again, our times have changed slightly. We will have sessions on Monday at 2 p.m. Eastern to 3 p.m. Eastern, and Tuesday morning, I should say the 11th, from 10 a.m. to 11 a.m. Eastern. We still have our normal Wednesday session, but that's the last session of the week as opposed to the first session. And we have a study guide linked here that also your instructor may have posted in your class or you received in an email. So we wish you luck preparing for your final exam. Next week, we will work on review problems for the final exam. And that's our focus to help you guys get ready for that. So good luck, and we hope to see you at one of our sessions next week. Thanks.